Hello everyone, this is Shinan from USTC and I'm Curtis from Virginia Tech. Today we're going to talk about how to use GPS spoofing to manipulate the road navigation systems in a stealthy way. This is a joint work between Virginia Tech, USTC, and Microsoft Research. By the way, since the session chair is not here, I'll just advertise for my fellow here. He is actually looking for an advisor and he is planning to do a PhD, so if you are hiring, just contact him. All right, let's get into the story. As you all know, GPS navigation is widely used around the world, and more recently, self-driving cars are relying on GPS for navigation and making critical on-road decisions. However, GPS malfunction can really lead to some real-world consequences, just like this. And as you may know, civilian GPS is vulnerable to spoofing attacks because they don't have any authentication schemes. I'll use an example to explain this. For example, there is a vehicle which is locking on the legit signals to calculate its true location. And here comes an attacker who transmits GPS signals with a higher power to take over the vehicle's GPS receiver and make it calculate another false location predefined by the attacker. Existing work have demonstrated successful GPS spoofing in free space. For example, in 2002, a drone was diverted in White Sands, New Mexico. And in 2013, a yacht was diverted on the way from Monaco to Greece. However, all these spoofing attacks only happen in free space, like open air or open water. If an attacker wants to spoof a vehicle on road and manipulate the road navigation system, it will be much more challenging. I will show this challenge with an example here. So on the left, you can see this is the real world. When you are driving, you see through the windshield. And on the right is the navigation map on the smartphone. So usually these two locations in the real world and in the navigation map should match each other. Here comes an attacker who manipulates the location to another spoofing location. And the navigation system will recalculate the route, which giving you instructions like go straight and turn left. However, in the real world, if you are trying to turn left, you can find there is actually no way for you to turn. So this is a physical impossible instruction, and the attacker will fail here. So as demonstrated by the previous example, we can see random or naive manipulations does not work in road navigation scenario because the attacker is not able to cope with road constraints like road shape and speed limit. So they can easily create some physically impossible routes. And moreover, if you are looking at the road navigation scenario, there are human drivers in the loop. So the attack needs to be as subtle as possible to avoid alerting human drivers. And we are the first to explore the feasibility of such an attack. Okay, first question, what's the stealthy attack? I'm reusing the previous example to show the stealthy attack. You have real world on the left and navigation map on the right. At this time, the attacker is more intelligent and he manipulates the victim to a specially crafted location as the green marker here. And the navigation system will recalculate a route, which gives you the instruction, go straight and turn right. In this case, if the victim exactly follows the instructions to go straight and turn right, then he will end up at another location predefined by the attacker rather than his original destination. So I'm going to introduce some concepts and the core idea to help you understand the stealthy attack. This is the actual location of the victim. And this is the original route from the actual location to the original destination. This is the ghost location, which is manipulated by the attacker. And this is the ghost route, which is calculated from ghost location to the destination. And if you are exactly following the instructions, the victim will travel through a victim route, which is shown as the black lines. As you can see, the victim route and ghost route have very similar shape, and the attack goal here is to find such ghost route to mimic the shape of the victim route. We have one assumption here, which is the attacker needs to know some rough destination area or checkpoint of the victim. You can get this kind of information by destination broadcasting in car-sharing apps and checking the victim's calendar accounts and location check-ins on online social networks. There are also some important check marks in a city, for example, the major highway entrances and the bridge and tunnels. We have formulated this stealthy attack into a route searching problem. First off, we have a map with intersections and road segments. Then we convert this map into a directed graph. The nodes are the intersections, the edges are the road segments. Then we run an exhaustive breadth-first search to search for the ghost routes and victim routes with two searching criteria. The first one is term pattern matching. So the term pattern in the victim route has to match the term pattern in the ghost route. For example, a left turn should match a left turn, and a right turn should match a right turn. The second criterion is segment length matching. So the corresponding road segments in victim route and ghost route should match with each other within a factor. If the attacker is not able to find a satisfying victim route in one round search, he can actually run iterative searching and concatenate the victim routes in different searching rounds to form a satisfying long victim route. So this searching ends whenever the attack goal is met. There are some consequences of the stealthy attack, which include but not limited to three kinds. The first one is deviating. So the attacker can detour the victim with no specific target destination. For example, he can delay the ambulance or police cars. The second one is targeted deviating, where the attacker tries to divert the victim to bypass a predefined location. And the third one is endangering, where the attacker can divert the victim to some dangerous situations, just like runway driving on the highway. To evaluate such stealthy attack, we have used the trace-driven simulation results, where 600 real-world trips are randomly selected from New York City and Boston taxi datasets. We run basic attack and iterative attack on this dataset. For the deviating results, on average, we have 335 and 35.7 qualified victim routes per trip for basic and iterative attack respectively. And for endangering results, we can get 599 out of 600 victim routes which contain runway road segments. These results indicate the attacker can have a very wide range of attack opportunities and can incur real danger to the users. For the targeted deviating purpose, in this case, the attacker tries to divert the victim to a predefined location. And we have defined one evaluation metric, which is called hit rate, to indicate how likely a predefined location is feasible. I will explain this with the example. So here is the original route of the victim. We first divide the map into grids with a certain size. And then we use a sweeping radius to sweep along the original route. Therefore, we can identify the candidate grids, which are the potential grids that can be diverted to by the attacker. Then we run our stealthy attack algorithm to find out which are the grids that can be actually diverted to by the attacker, and we call them diverted grids. So the hit rate is calculated as the number of diverted grids over the number of candidate grids. For the results, we can have a 70% median hit rate with 500 radius in Manhattan for just basic attack. These results indicate even for a random predefined location, it is highly reachable by the attacker to divert the victim to. So now we have already proposed the stealthy attack. We are wondering, would it be possible to actually implement the attack in the real world?
So in order to answer this question, we actually made our own spoofer and conducted several real-world experiments to validate the capacity of the state-of-the-art GPS spoofer, as well as our attacking algorithm. We made this low-cost portable GPS spoofer based on several hacking projects. As you can see, it is comprised of 3 parts. A Raspberry Pi, which is in charge of generating fake GPS signals. A HackRF1, along with an antenna, which is the SDR platform that is responsible for transmitting the signal, as well as a mobile charger, which provides energy for this tiny gizmo. So we can actually use cellular or Wi-Fi to remotely control this device. And all of the components can be easily bought online with a relatively low price, like $223 in this case. And as you can see, the device is really small, so we can put it inside a handbag, which makes it even more stealthy. Notably, we have taken very active steps to ensure the legality and research ethics. All of our experiments are exclusively done in China. We did not do any spoofing test in America. So we actually got a temporary permission from Chinese local authority. And we also got an IRB approval. For the spoofing capability test, we actually did a lot of controlled measurements after midnight with no cars around. For the end-to-end system test, we also performed a very strict power control to ensure that no one's affected. So how can we use the device to attack? Here are 2 possible means. Leaving the spoofer inside the victim's car or tailgating the victim at a distance. So in the same car setting, we put an Android flagship phone in the dashboard. Then we put a spoofer underneath the backseat or in the trunk. So in this setting, we actually achieved an average takeover time of around 40 seconds. And in the 2-car settings, however, we vary the distance between the spoofer and phone. Actually, we've achieved a similar takeover time, and the effective spoofing range is 40 to 50 meters. We also check the consistency of the signal. It remains it's the same to latch on, even when we are dynamically driving the car, and there are also some kind of car body blockage effects. Yeah, so the controlled measurements actually showed the capacity of a real GPS spoofer. We also use this real-world driving test to show how our end-to-end system works. So the attack setting is basically a same car setting, and 2 of our authors participated in this attack. We drove our own car, and 1 author strictly follows the navigation instructions, and the other author sat on the back seat and operates the spoofer and then run our attacking algorithm. So we've tested on those 2 different routes. The instructions were triggered in time, and the cars were diverted away to 2.1 and 2.5 kilometers. So actually, we've tested and demonstrated that the GPS spoofing attack is very powerful. But what if the human factors that are involved? Can human users actually detect it?
Okay, to answer this question, let's get into the user study part. So the user study is performed with a driving simulator, and we let the users drive in the simulator. They are playing truck drivers to deliver packages from location A to B, and we see if they can be diverted without noticing the attack. So the users will think this is for software usability testing. And this is the experiment setup with a big screen as the front view and a smartphone on the side as a navigator. This is the simulated view, and this is the corresponding Google Street View. You can see this is very realistic. And we also build a software to spoof locations in real time. The spoofing will be this attack will be ended whenever the user recognizes the attack. And after the driving simulation, we do a complementary survey and interview to know why the users can or cannot detect this attack. We will tell their true purpose and obtain their consents. There are more details and a demo video in the paper. There are some key results drawn from our user study. The first one is for attack success rate, which is 95%. There are only 2 users who have detected it by cross-checking the surrounding environment and navigation map to find some inconsistency. For example, one driver actually detected the attack because he realized he is driving on the highway, but the navigation map shows he is driving on the local way. This is a very big discrepancy. And the second one is users are more likely to use GPS in unfamiliar areas. This is very intuitive but critical to our attack because the users do not have enough pre-knowledge or time to check the inconsistency. And the third one is that most users have experienced GPS malfunction in their real life. That's why unstable GPS signal does not alert users. So to recap our work, we have explored the feasibility of stealthy manipulation of road navigation systems in 3 steps, which are route searching algorithm, capability measurements, real-world driving, and human-in-the-loop user study. As inspired by the user study results, a potential difference might be using sensor fusion for cross-checking between the physical environment and the navigation map. Compared with this solution, other solutions like encryption, infrastructures, modification for hardware and software have much higher cost and longer deployment cycle. That's our talk. I'm very happy to take questions.
Thank you. If I could ask, please use the microphone.
Hello, Michael Brotzman, U.S. government. I just have a question. You did your taxi cab study in Boston and New York. Do you have any idea how your sort of reachability and divertibility would work in an area with less regular roads, like a suburban setting or rural, where it's not like a grid?
Yeah, that's a very good question. So definitely our attack will have the best performance in very high road density cities like Manhattan, Boston, like that. If the attack is performed in suburb area, it still gives you a decent probability. If the attacker is not able to reach his predefined location, then he can run multiple iterative searching. Actually, we have observed when you run one more iterative searching, it gives you a bump of the hit rate by 20%. So that's how you get your satisfying victim route in the less denser road density cities.
Is there any additional data in your paper, or did you not have that yet?
You mean additional tests for other cities other than
for other areas?
For other areas other than Manhattan and Boston?
Oh, yeah, just those two?
Yeah, right now just those two, but it's pretty easy to run on other cities. You just download the OpenStreetMap for the targeted area and run this algorithm. You can see what's the hit rate and derivative.
So when you do, I'm Yongde Kim from KAIST. So when you do GPS spoofing, physical GPS spoofing, did you have to jam it first and then spoof because you need to take over the signal?
Yeah, that's another very good question. So that actually depends on the capability of the spoofer. For our spoofer, it's a very low-end brute force spoofer. So if we use this spoofer to brute forcefully transmit false signals, it will act like a jamming at first. So the device will just lose the legit signal, and after 30 to 40 seconds, it relock on the false signals we transmit.
Right, that means actually user may notice that actually the GPS lost the signal first, right?
Yes, for our spoofer, it will cause this GPS signal loss. Actually, we have simulated this signal loss in our user study. So we observe when human drivers encounter this problem, they basically keep driving and go straight until the signal come back, and then they follow the instructions afterwards. Okay. To add on, there are more high-end spoofers which can actually synchronize with the legit signal and do some seamless spoofing without causing any signal jump or any loss on the spoofer, on the victim GPS receiver.
Thanks for the talk. My name is Shinan from University of Washington. Actually, that's the questions I just want to ask. But I have one more question. So when you transmit the spoofing signals during takeover, what's the spoof signal, spoof location you're using? Are you using a location next to the kind of the true location? And also, are you using the real affirms data for simulating the GPS signal?
Let me rephrase your question. Are you asking when we are taking over the GPS in the very beginning, which location we set as a starting point?
Yes.
That's actually one of the design in our algorithm. So that's the ghost location you are looking for. We have defined a shifting constraint for the attacker to move the real location to a ghost location. So the ghost location is within 400 meters of the actual location of the victim.
Okay. So second question is, are you using real-time, most updated kind of affirms data, or you're using old affirms data, or generated affirms data?
You need to use the up-to-date ephemeris data, otherwise your device will not lock on it. That's one time we failed to take over the GPS device because we forgot to use the update ephemeris data. So you can download the most up-to-date ephemeris data from the network.
So it's like, in the previous 24 hours, what's the time lag? You can't get it real time, can't you?
Oh, you don't have to get it real time. Ephemeris data is 4 days, 4 hours at least. So you don't have to be like precisely every second get the updated ephemeris data. Ephemeris data is actually giving the receiver the information that which GPS satellites I need to lock on at this moment. So it will fasten the locking on process because the receiver already knows which GPS satellites on the sky I can see and I can look for to lock on.
Okay, thank you.
We have time for one very quick question.
Justin from Ford. The systems that you were testing, were they standalone navigation systems such as a cell phone or portable navigation system?
You mean which navigation systems we have tested in the experiment?
Yes.
So we are testing mostly the smartphone navigation system apps.
Okay. So you didn't test against any in-vehicle navigation system that takes other sensor data from steering wheels or?
Yeah, that's true, and that depends on 2 factors. 1, how capable is your spoofer? 2, how capable is your navigation chip can defend against such spoofing attacks? So it varies from device to device, chip to chip, spoofer to spoofer.
Okay.
So join me in thanking our speakers.
Thank you so much.